Hello, this is Miraj Patel, and today we're going to be talking about the 5 different types of reactions, and this will be the last unit for Unit 8, which is all about chemical reactions. And so here are the 5 different types of reactions. We have synthesis, decomposition, single replacement, combustion, and double replacement. And so on this next slide here, we have a diagram of all of the 4 types of reactions. This just doesn't include combustion, so that's the one that's missing from here. And so don't worry about this, we're just going to be talking about this throughout the whole PowerPoint. And so here's the first reaction. We have synthesis, and you could think of this as the marriage. So in a marriage, there's one boy and one girl, and pretty much they just get together and voila, you have a couple. And so that's the same thing in synthesis. You have 2 different elements or compounds, and then they combine and form only one product. So that's the important part. In synthesis, there's only one product. And if you don't want to use this marriage example, you can just think about synthesizing something. So if you synthesize something, you make something. When when your teacher says synthesize a paper, so that pretty much means you take in a bunch of different, facts if you're doing a research paper, and then synthesize one whole product. So synthesis just is a fancy word for means like combining a bunch of parts and making one new thing. And so a good example is the formation of water, which is 2H2 plus O2 equals 2H2O. And the reason, again, just to review, the 2's are here because these are diatomic elements. Remember the lucky 7. So synthesis, again, is just the combination of 2 different elements to make one product. And now we have decomposition, which is like a breakup or a divorce. So we have a couple here, and then pretty much they don't want to be with each other no more, so they break up into separate components. And so same thing as this little analogy, we have A, B, so 2 different elements bonded together or compounds. Then when they break up, they form A by itself and then B by itself, like this. And then the important part about this is that there's only one reactant. And again, if you don't want to use this marriage analogy, you can just think about decomposing. So when you decompose something, just like in biology, those little fungi that decompose things, they break them up. So just think about decomposition or the breaking up of something. So same thing in this one. One big chunk breaks up into 2 separate pieces, just like decomposition. And a good example is the decomposition of hydrogen peroxide, which is H2O2, that chemical that's in that big black bottle, usually found underneath in like kitchens and bathrooms. So this pretty much just kills bacteria, or it's antiseptic. And so this breaks down into water, H2O, and then O2 because of light. So pretty much that's why it's in a dark bottle, so to protect it from light so it doesn't decompose into this. So next time you know that hydrogen peroxide decomposes, or is a decomposition reaction, into H2O and O2. And so here we have single replacement, or the kick out. So pretty much in this example you can see that there's one guy by himself, and then he wants to be part of this couple, where he wants to be with this girl here. And so pretty much he gets into the couple, but then this guy gets kicked out. And for some reason this guy is just smiling at this couple because he doesn't care really anymore. So it's just pretty weird. All these people are just happy, happen to be happy. Maybe it's just a happy world. And so the main point is, in a kick out, one loner element goes and kicks out another element and replaces it. So we have A, which replaces B in this reaction, and it forms AX plus B. And so a good example is like a bunch of ionic compounds. So we have Mg here, so magnesium, and then two hydrochloric acid, so HCl. And so this magnesium pretty much goes and kicks out this H, and it forms MgCl2 plus H2. And so in single replacement, remember, one element kicks out another. Then we have single replacement, but the important part about this reaction is that the more active metals will replace less active metals. So in these examples, we can see that there's an element here that replaces this one and forms this thing. So in order to react, this metal outside has to be more reactive than this metal that's already bonded. And so in this one, potassium is definitely more reactive, you can tell, because it reacted. So if it doesn't react, it's less reactive. So potassium is definitely more reactive than copper because it replaced it. Lithium is definitely more reactive than potassium because lithium replaced potassium here. Notice how lithium went with Cl. But look at this, because copper here does not replace lithium, and so it forms no reaction because copper is not strong enough to kick out lithium. So if you look at this, you can tell which metals are more reactive by comparing them. So definitely we know that potassium is more reactive than copper. So, and then copper is less reactive than lithium. So if if potassium is more reactive than copper and lithium is more reactive than copper, that means copper has to be has to have the least reactivity. So, and also by looking at this, you can tell that lithium is more reactive than potassium because it reacted with uh, potassium chloride, and lithium is more reactive than copper. So lithium must be the most reactive than these two. And then, because we know that copper is the least, that means potassium has to be in the middle, because potassium can kick out copper, but lithium can kick out potassium. So that's how, if you, on a test, you might have a question where it gives you three reactions and three different metals, or, positive cations, and it asks you which one's the most reactive, and you can tell by seeing which one replaces which. So remember, more active metals will replace less active metals, and same thing vice versa. So less active metals will be replaced by more active metals. Okay, and so here we have a list of reactive metals, and the cool part about this is this actually does check out on this list. So here we have lithium as our most reactive, and it is in fact the most reactive. Then we have potassium next, and look at that. Underneath lithium, there's potassium, and then we have copper, Cu, which is all the way down here. So this is actually true. And so you can get this little trend from looking at three equations and seeing how the metals react. So if it kicks out, it's more reactive. But if it can't be kicked out, that means this metal bonded is more reactive. And so here we have the fourth reaction, which is combustion. And a combustion is just a scientific word for burning. And so combustion, the unique thing about its reaction is it always has as a hydrocarbon, or a carbons and hydrogens bond together, and X and Y just represent random numbers. And this hydrocarbon here reacts with oxygen and always forms CO2 and H2O. So if you see CO2, H2O, and O2 and some hydrocarbon, that means it's combustion. And so a good example is C3H8 and 5O2 equals or yields 3CO2 and 4H2O. And so notice how there's carbon and hydrogen, or hydrocarbon, and then oxygen, and then it yields CO2 and H2O. So if you see CO2, H2O, on the products and O2 and a hydrocarbon on the reactants, it's always combustion. So just remember that. And so the important part is these four reactions are all redox reactions. And if you remember, redox reactions stand for reduction and oxidation. So all these reactions, there's oxidation reduction happening. And so here's example. So we're showing the charges so you can tell. So here we have a neutral charge, but then we have charges when they bond together. Because if you remember, when atoms or element compounds from octets, they slightly change their charges because they give away or lose. And so, and so, synthesis is definitely a redox reaction because the charges change from neutral to charge. Then we have decomposition, which is from charge here to neutral. And so again, in all these examples, they're just examples of synthesis, decomposition, and stuff like that. And so then we have single replacement. So we have a neutral element here, and then we have a charged compound. But when this neutral element gets into a compound, it gets charged. And so an example would be like Zn or zinc and HCl. So zinc replaces the H in Cl, and then after this it becomes charged, and then the H becomes neutral again. Then we have combustion, and so notice how we have carbon with a negative charge and then carbon with a +4 charge. So it definitely changed charges. And so then hydrogen stays the same, but oxygen is neutral but then becomes negative. So there's definitely a -2 in both. And so there's definitely a charge change. And so this is why all these reactions are redox reactions. And then we have the fifth type of reaction, which we haven't talked about, is double replacement. So pretty much this is just like switching partners. So we have these two couples, and so pretty much the two girls switch. And so this girl ends up with the guy in the wheelchair, and then this girl ends up with the guy with the flat haircut or purple shirt. And so pretty much these two just switch. And so here we have just a little equation. So we have AX and then BY equals or yields AY and then BX. So pretty much the two X and Y just switched. And so the two compounds pretty much just switch ions or partners. So example would be like we have potassium iodide and then lead nitrate, I think, NO3. And then this NO3 is together, and so the NO3 goes with the potassium, and then the lead ends up with iodine. And so the iodine just went here, and then this one went there. And the important part is this is not a redox. This is the only type of reaction that is not a redox. So remember, not a redox. Not a redox. Double replacement is not a redox. So if you have any other type of reaction, it's a redox, definitely. But this one's not a redox because they switched partners, and once they switch ion partners, they just, again, they become equalized. So remember how ions, they're always neutral. So both elements are always together form neutral. And so once they switch partners, they're still neutral. So just remember that. It's not a redox. And so here's a quick quiz to see what you learned. Which type of reaction is described by the following equation? So we're just gonna go through the reaction, figure out what it is. And so we have lithium and nitrogen, and then they combine like together, and they form 2Li3N. And so we have two reactants and form one product. So if you remember, synthesis is the combination of multiple things to form one whole product. And so just like when you synthesize a paper, or just think of the marriage example, we have one one boy, one girl, and then they become together and they become a married couple. So just think about synthesis. So this is definitely a synthesis because two little elements became one whole compound when they combine. And is this a redox reaction or not? And if you remember, just from what I said, everything except double replacement is a redox. So if this is not a double replacement, that means it's not a, if it's not a double replacement, that means it's a redox. It is a redox. So this is definitely redox. Then here we have question 2, which type of reaction is described by the following equation? So we have Mg2HNO3 yields MgNO3 2 and H2. And so pretty much it's either synthesis, decomposition, single replacement, or double replacement. So we have Mg here, magnesium, and then we have H, and then NO3s together. So just imagine that there's parentheses here. And so pretty much the Mg switches with the H. And so if we have one loner element and a little couple here, and then this loner becomes part of the couple, or becomes a part of, and kicks out one other person. So this would be an example of a single replacement because one element here is replaced by one. So you can just think about how the analogy, the marriage analogy, that there's one couple and one not in a couple, and so it just pretty much just cuts in. Or you can just think about the name, single replacement. One element is replaced by another. So the answer is C. And again, is this a redox or not? And if you remember, the only type of reaction that is not a redox is double replacement, so this must be a redox because it's not double replacement. And so here's the third question. Which type of reaction is described by the following equation? So we have 2C2H5OH plus 7O2 yields 4 CO2 and 6 H2O. And so just by looking at this equation, you can see that there's a bunch of carbons here, C2, and then we have a bunch of hydrogens here, and then we have oxygen with it reacting with it, and it forms carbon dioxide and water. So what does that tell you? Just from looking at these two and this and just seeing this, you can tell that this is definitely combustion because you see the hydrocarbon here, we have oxygen, they react together and they form carbon dioxide and water. So this is definitely combustion. And again, is this a redox or not? And if you said yes, this is definitely a redox because if you just remember the golden rule, if it's not double replacement, then it's redox. So if the only time it is not redox is if it's double replacement. And so here we have question 4. Which type of reaction is described by the following equation? So we have lead nitrate, and then we have NaCl, or sodium chloride, and then pretty much the lead switches partners, so it becomes bonded to the Cl here, so this NO3 switch, and so then we have Na and then NO3. And so here we have two bonded couples, or two couples, and they pretty much just switch partners. So if it's not synthesis or decomposition, because synthesis, everything comes together and forms one product. In decomposition, there's one whole reactant and forms two products. So in this, if you think about two couples and they switch partners, it would be an example of double replacement because two elements replaced each other. And so is this a redox? And this time it is not a redox because double replacement is the only reaction where it's not a redox because when they switch, they equalize their charges, and so they end up having no charge change. And then here we have question 5. balance this equation, describe it as a combination or synthesis or decomposition reaction. And so we have H2SO4 yield H2O2 and SO2. And so here we can first do the first step. So we have to balance this equation. So is this balanced? So first we have to count the number of atoms on each side. So we have two hydrogen here, check. We have one sulfur here, check. We have 4 oxygen here. We have 2 oxygen here. That doesn't look balanced. But if we look at this oxygen, there is 2 here. So there's 2 plus 2, which is 4. So this is definitely balanced. So if you got like thrown off by the little split in oxygen, don't worry. Just remember, count all the oxygen. So there is definitely 4 oxygen. So this is definitely balanced. So this is perfect. So we should just leave it alone. And so this is definitely wrong because there's a coefficient of 2. So these two, C and D, you can eliminate immediately. And then, is this decomposition or synthesis or combination? Combination and synthesis are the same thing. I forgot to mention that. Combination is just like synthesis. Just think about combining things. If you combine things, you put two things together, just like synthesizing. So if we have one reactant form two products, it's definitely breaking up or decomposing. So this is definitely decomposition. So again, think about like fungi and how they break up different, compounds and like break it up into down to soil. So they turn complex things into simpler things. And then you can think about it just like a divorce. So you have a couple here, and then you break them up into the two people. And is it a redox or not? And so if you said it is a redox, you are correct again. And so you're probably tired of hearing this, but only type of non-redox reaction is double replacement. That is not a redox. Everything else is redox. So if you had to guess, just guess redox, unless you have double replacement, which is definitely not a redox. And so that is it for Unit 8 and this video. And so let's just quickly go over Unit 8. So we have reactions. And so in reactions we have reactants and products. Reactants are before the arrow, and then products are after the arrow. And so when we're balancing equations, you have to make sure that both sides are equal, because we have to follow the law of conservation of mass, which says that the sum of the reactants equals the sum of products, like the masses. And so when we balance equations, you have to make sure both sides have the same number of atoms of each type. And so we do that by adding coefficients. And so you always have to make sure they're always balanced and keep track of all the changes so you can balance everything together. Then we talked about redox reactions, which just stands for oxidation and reduction. And so oxidation, remember, Leo says Ger. So Leo, lose electrons, oxidation, and then gain electrons is reduction. So remember, like nonmetals like to reduce or get reduced, so they gain electrons and they become more negative. Metals, on the other hand, like to get oxidized, so they lose electrons and get more positive. So if you lose something negative, you get more positive, and if you gain something negative, you get more negative. So think about reduced, you get a lower charge. So reduced, lower, oxidized, bigger charge. So that's a good way to remember that. And then we just talked about the 5 different types of reactions. So let's see if we can name them. We have synthesis, which is just like a marriage, combination of 2 different elements to form a compound. And it can also be called a combination reaction. Then we have decomposition reaction. And so it pretty much breaks up a marriage. So we have a married couple, and then we divorce them and break them up into the 2 separate people. And then we have single replacement, which is one loner pretty much kicks out a bonded pair and pretty much gets married, but the other guy gets kicked out. And then we have double replacement, which is when we have two couples and they switch partners and they form two new couples. And then we have combustion, which is always a hydrocarbon and oxygen reacting together to form CO2 and water. And so remember, combustion is just burning, so just think about fires. And remember that the only non-redox reaction is double replacement. Everything else is redox. So remember, everything is redox except double replacement. And the reason why double replacement is not redox is because they just switch partners, so they become equalized again. And that is it for Unit 8. And so Unit 9, which is the next video, is all going to be about stoichiometry, which is all about balancing and finding grams and moles of different substances in chemical reactions. So we're going to do a lot of converting there. So until next time, I hope you have a good day, and we'll see you later.